You've got these two unfortunately named siblings, and they're making shirts, okay? Joe is like me. He's a bit slow, okay? He takes his time, but he's quite accurate. He's got a 98% flawless rate, okay? Only 2% of the shirts he ever makes are defects, okay? Faye is faster. She's a whole 50% faster, okay? But she makes twice as many errors as Joe does, so 4% of the shirts that she makes on any given day, they are defects, okay? So then, here comes the question. What they do is they bundle up all of the shirts they make, they bundle them into boxes of 30, okay? Out they go, 30 each. Well, obviously they're going to do more than one a day, but each box that goes out to the warehouse is 30 shirts, okay? So the question is, what is the probability, right, that no more than 2 shirts in the box, are defects, right? So I would write it like this. Because, if there's more than 2 shirts, if there's 3 or 4 or 5 shirts in there that are bad, the company's going to send it back and say, this is rubbish. You must be joking. Get it? Anyway. So we want to think about... It's the last one. I have to make it worth it, right? We want to think about, well, what's the how likely, given this kind of error rate, right? How likely are we to get under this threshold? What's the probability that no more than 2 shirts will be defective? Okay. Now, the first big clue is, okay, this is a binomial probability question. This is a good candidate. You don't have to do it by binomial probability, but it's a good candidate for it. Okay. Because you got 30 shirts. Do you really want to draw a probability tree for all 30 shirts? Probably not, okay? But then, how do you... You've got to phrase it the right way, don't you? Okay, it's multi-stage, that's easy, okay? There's got to be 2 outcomes. You can probably think about what the 2 outcomes will be. But because they're both in the situation, it makes it a little more tricky. So why is this harder than a normal binomial probability question? Okay, I'll tell you why. Let's come back to how you know. Here's how you know a question is a binomial probability question. Okay, it's multi-stage. Well, that's fine. You got to pick 30 shirts. No big deal. Okay, there need to be just 2 outcomes that we're interested in, or you must be able to phrase it in some way so there's only 2 outcomes. What would they be? Defect or not defect? So, no problem, okay? But then, in order to make it work for binomial probability, you need every event to be identical. But there's a problem with that, right? Because when you open up the box of 30 shirts and you pull one out, you don't know who made the shirt, right? So you don't know then which one of these will take over, okay? So you're like, how do I make the events identical, okay? Well, you come back. When you pull one shirt out, okay, it's true enough that you don't know, wow, look at that, anatomical accuracy. You don't know who made the shirt, but you know who was likely to make the shirt, and you know how likely it was who made the shirt. Because of course, there are only 2 options, right? It's either Joe or it's Faye, okay? Now they make it at a consistent rate. So even though I don't know whose shirt I actually pick up, I know that in a day, how many shirts are made? In a day, 50 shirts are made, right? 20 of them are Joe's. 20 out of 50 shirts are Joe's, right? Whereas the other 30 are Faye's. Okay. Now, we can come back to this idea. Defect, not defect, right? For each of them, they will either make a defective shirt or not a defective shirt. So you have these options. Okay, and we know the probabilities for each one, right? For Joe, it's going to be 0.02, 0.98, 0.04, 0.96. Okay, so now we can come to trying to build an identical event. We've got enough information now, okay? We're interested in the defects, right? So, looking at this situation, right, there are only 4 kinds of shirts you can pull out. They're not all equally likely. Clearly, they're not all equally likely, right? But you can know what their probabilities are. For instance, what's the probability of one of Joe's defects? The answer is, well, product rule, 20 on 50 times 0.02, 1 on 50. Right? So you work out what that is. And then you've got the probability that phase will be a defect, right? And you work that out, okay? So now, the probability of any single shirt being a defect, right? So this is our identical event which we can just repeat over and over and over, right? It's going to be, well, I have to combine these. Do I add them or do I multiply? I must add. Clearly, I must add for a couple of reasons. Firstly, if you did what I did and you drew out a probability tree, right? Adding and multiplication only go in certain ways. Multiplication goes along the branches of a tree, right? Whereas addition goes up and down, right? Does that make sense? So that's an easy diagrammatic way where you can work out which one's which. In terms of logic, you can think about it this way. I'm pulling out how many shirts to look at them? Hold on. Just for this, I'm pulling out a single shirt, right? So who made the shirt? And the answer is Joe made it, or Faye made it, but they didn't simultaneously make the shirt, right? So if they're not simultaneously, I have to add. Okay? So the probability of Joe's defect plus the probability of Faye's defect. Okay? Now when you put that all together, I think you end up with 4 on 125. That's our event. Now, that's our probability of our event. You can obviously work out what the complement is, which you'll need in a second, which will be the remainder. Whoops. Okay, so now I've set up my identical events, and now the binomial can unfold. Okay, when you have a look at this, there are a few different ways that this can happen, right? There are a few cases. What are the cases? Give me one. No defects. Great. 0 defects. That's one way that we can satisfy this. Okay. There's another way. 1 defect. Again, I'm adding these because a box can't have 0 defects and 1 defect at the same time. And then of course there's one last case. 2, because I'm okay with the boundary. I am still no more than 2 defects. 0, 1, or 2. Okay? And then you work out each one in turn. How do we do the first one? There's 3 components, right? There's 3 components. How many ways are there to have no defect? The answer is 30, choose 0. Right? That's how many ways. And now I work out the probability. What's the probability of a defect? It's that, but there aren't any defects in the box. So I do that 0 times. Right? And then I want all the other shirts, that's 30, to have no defect. And you can recognize this in terms of the general rule we developed this morning. Okay? And then you do the rest of the cases. So 30, choose 1. There's our 1 defect right there, the probability. Our other 29 shirts, which are all good, and their probabilities. And then your third and last case. 2 defects. 28 good shirts. Okay? You add it all up, and it's not that bad. It's 93%, roughly, to the nearest percent. Okay?